good morning. So I'm Anrin from UIC, and this was work done while I was a postdoc at Duke University. So I'm going to talk about distance-aware private set intersection, which is a variant of the PSI problem. And this is joint work with Giulia Fanti from CMU and Mike Reiter from Duke University. So as you have probably heard several times today, PSI is a very well-studied cryptographic primitive with many applications. And at a high level, the PSI functionality takes as input sets of items from 2 or more parties, and it computes the intersection of these 2 sets, and it returns to 1 or more of more parties the items that end up in the intersection, but crucially, it does not reveal any information about the items that are not in the intersection. And there are many different ways in which you can implement this functionality securely and efficiently. So all of these PSI protocols are great when you want to compute an intersection where you are performing exact matching of items. But they are limited in their functionality in the sense that if you want to compute an intersection based on some similarity metrics, these protocols do not really scale that well. So in this work, we have introduced a new variant of the PSI problem called distance-aware private set intersection. So the distance-aware PSI functionality takes as input sets, but the items in these sets are vectors that are drawn from some arbitrary dimension metric space. And in addition to these vectors, the functionality also takes as input some parameters, which includes distance threshold denoted by the letter T, a false positive rate, and a false negative rate. And I'll explain in a second what these parameters do. So with these inputs, the functionality returns an intersection of the sets to either 1 or both of the parties in such a way that pairs of vectors that are closed in the metric space end up in the intersection with high probability. And by the same logic, the vectors that are not closed do not end up in the intersection with high probability. And here, closeness is defined based on your distance threshold, which means that we say 2 vectors are close when the metric distance between these vectors is less than the defined distance threshold. So one obvious question could be, why do we want to build a primitive like this? So we have explored several applications in the paper, and we have actually applied these, applied our protocols to these applications. This includes things like collaborative threat detection, where multiple organizations who are mutually untrusting share identifiers of compromise or IOCs with each other in order to detect attacks from the same entity. And in these cases, these IOCs tend to be high-dimensional vectors where you need to perform some similarity matching in order to detect attacks. We've also applied our protocols to performing queries on biometric databases, and we've also explored how these protocols can be applied to detect credential stuffing of similar passwords across multiple websites. So in general, if you have an application where you're embedding items in some metric space and you want to compare similarity between these items, distance-aware PSI functionality is going to be useful. Before I get into kind of discussing how our protocols work, let's formalize this problem setting a little bit more. So we are going to mainly build protocols that are 2-party protocols where the parties are assumed to be semi-honest, which means that they follow the steps of the protocol correctly. We are also going to rely on standard cryptographic assumptions. Wherever possible, we are going to try to rely on symmetric key primitives, which means that while we can realize this functionality with generic secure computation tools like fully homomorphic encryption, wherever possible, we'll try to rely on something more efficient. So for those of you who build cryptographic protocols for a living, you're probably thinking, okay, this does not sound like a very challenging problem. The only thing we need to do here is compute some distances between vectors, compare with a distance threshold, and just kind of return a 0-1 result. And that's it. This is where the problem gets a little bit interesting, because we are going to add an additional constraint on our protocols here, where we want to build protocols with costs that scale sublinearly in the number of dimensions. And by cost, I mean the compute costs as well as your communication volumes. And there are some very good reasons why we want to do this. In all the applications that we have been looking at, it tends to be that we have to compute on very high dimensional vectors. And in general, this is true for applications where you are embedding items in some kind of a metric space with tools like locality-sensitive hashing, where it tends to be that the accuracy of your system directly depends on the number of dimensions of your vectors. So it would be nice if we had some protocols where the cost of the protocol scale at least independent of the number of dimensions in the best case, or at least in the average case, sublinearly in the number of dimensions. So we have also discussed in the paper why this is hard to do with existing tools, but in the interest of time, I'm not going to go into details here. So if you want more details on this, I encourage you to take a look at the paper. So based on these constraints, we were able to come up with protocols for 2 pretty widely used distances. So our first protocol is for Hamming distance. And in this case, the online cost of our protocol scales quadratically in the set size and the distance threshold. But importantly, it's independent of the number of dimensions of the vectors. And in the applications that we've been working with, the distance threshold tends to be significantly smaller than your number of dimensions because we are looking for closed vectors in a pretty large space. And this protocol can be realized simply with OLEs, which is a pretty fast primitive. Secondly, we've also built a protocol for Minkowski distance of order 1, which in simple terms is just the absolute difference between two integers. And in this case, the online cost of our protocol scales linearly in the set size, which is optimal for PSI, and it scales logarithmically in the distance threshold. And an interesting feature of this protocol is that you can build this protocol on top of any existing state-of-the-art PSI protocol. So if you know how to do fast PSI, you know how to do fast Minkowski distance-aware PSI. So in the interest of time, I'm going to mainly focus on the Hamming distance protocol here, but if this talk has piqued your interest, I encourage you to take a look at the paper for the Minkowski distance-aware PSI protocol. So in order to build a Hamming distance-aware PSI protocol, we have to solve a sub-problem here, which is equivalent to solving this problem for singleton sets. So this problem is that given two vectors, or binary vectors, how do we privately check that the Hamming distance between these two vectors is less than some threshold value t with communication and compute costs in the online sense sublinear in the number of dimensions of the vectors. So because of this sublinearity requirement, we can't actually compute the Hamming distance between the vectors, so we try a different way here. We estimate the Hamming distance from set difference. And the way this works is that, say Alice and Bob have these vectors that you see on the slide. They first derive sets from these vectors. And the way these sets are derived is that each element in the set corresponds to a bit in the vector, and each element is a tuple, where the first part of the tuple tells you the location of the bit, and the second part of the tuple tells you the value of the bit. Now, one thing you can observe from the example here is that the Hamming distance between these two vectors is actually the cardinality of the set difference between these two sets. And this is in general true for any two vectors of the same length. So this is an important observation because this allows us to ask an equivalent but different question, which is, can we privately compute the set difference of two sets where we know that the cardinality of the set difference is less than some threshold value with costs that are sublinear in the set sizes? And it turns out that we can do this with a protocol due to Ghosh and Simkin from Crypto 2019. And a great feature of this protocol is that the online cost of this protocol scales linearly in the threshold, independent of the set sizes. So this is a good starting point to build a Hamming distance-aware PSI protocol. And I'm going to give you the high-level steps of how this protocol works. So I'm going to describe this for singleton sets, but you can generalize this for sets of arbitrary sizes by running pairwise comparisons, which will give you the quadratic complexity in the set size. So the way this works is Alice and Bob start with these vectors, and they derive sets from these vectors, as I mentioned before. And then they derive polynomials from these sets, where each element of the set is a root of the polynomial. Then they evaluate these polynomials at order of t points. These points are public information known to both Alice and Bob. Then they interactively evaluate a random combination of these polynomials. And Alice gets the evaluations of these polynomials, which she can then interpolate. And the guarantee that you get here is that if Alice and Bob's set have less than t differing elements, then Alice can uniquely identify Bob's set. But if there are more than t differing elements, then this combination polynomial completely hides Bob's set from Alice. So casting this to our Hamming distance problem, what this means is that Alice will learn the vector b when the Hamming distance between a and b is less than the threshold value, but otherwise she's going to learn no information about this vector. And Ghosh and Simkin have shown how we can implement this box interactively with order of t communication using OLEs. So in principle, we should be done at this point of time, but unfortunately, we are not. Because when we analyze the security of the protocol, we find that we get security, but with caveats, which means that this protocol is secure, but only for a certain set of parameters. So what this means is that when the Hamming distance between two vectors is less than the threshold, then this protocol correctly returns the result. It indicates this to both Alice and Bob. When the Hamming distance between these vectors is less than twice the threshold, then again this protocol works correctly and it does not reveal any information. But when the Hamming distance between A and B is between the threshold and twice the threshold, then this protocol reveals some information. And unfortunately, this leakage is inherent to the protocol of Ghosh and Simkin, and they have informally mentioned this in their paper, but we have actually formally quantified what this leakage is. So there is no way to get around this problem without redesigning this protocol. And we were able to solve this problem not in actually one way, but actually two ways. So we came up with 2 different protocols with different trade-offs. So our first protocol trades off some accuracy in terms of incurring some false positives. And in this case, what we do is we use a probabilistic approach to eliminate these problematic inputs, which means that if there is some input in Bob's set where the Hamming distance between Alice's vector and Bob's vector is between the t and 2t, then we eliminate this before running the set reconciliation protocol. And we make sure that these steps are integrated indistinguishably, which means that if you do eliminate some problematic inputs, Alice does not know about this because that would not satisfy our functionality. Secondly, we were also able to build a protocol by leveraging compute costs. So we were able, what we observed is that the protocol of Ghosh and Simkin will also work if you provide some less information to Alice, which takes care of the leakage, but it requires some additional compute costs from Alice's end. So I'm not going to go into the details here. The math is a little bit more involved. But if this is of interest to you, I encourage you to take a look at the paper. So we have implemented our protocol, and we have benchmarked this in terms of how communication costs, compute times scale with the vector lengths, the distance thresholds, and as well as the set size. And what you see here are some micro benchmarks where the communication cost and the compute time scales with the number of dimensions of the vector. And our baseline here is a garble circuit implementation of just a simple distance-aware PSI protocol based on the protocol of Huang et al. From USENIX Security 2011. So what we observe here is that for small vectors, the garble circuit baseline actually performs better, but for larger vectors that you usually see in your application of 1,000 bits or more, the distance-aware PSI protocol performs better. And in fact, when you have vectors of around 8,000 bits, which you get in things like biometric authentication, distance-aware PSI has almost 11 times lower compute costs. We've also compared with a state-of-the-art system for performing queries on a biometric database. And this system is a fully homomorphic encryption-based system by Ozun et al. From USENIX Security 2021. And here we compare how the communication cost and compute time scales with the set sizes. And both in terms of compute time and communication costs, our protocol performs better than this state-of-the-art protocol. So in conclusion, this paper presents a new variant of PSI with some real-world applications. We have provided protocols for Hamming distance and Minkowski distance. But this is a growing space. There is a lot of new research opportunities and open problems here. So stay tuned to this space for more results in the future. So thank you, and I'll be happy to take questions.